Next up are stretches. So if you look at an x prime, you're moving it to some kind of factor times the original x, and the new y prime stays to the same y. So if you rewrite these, it's going to be kx plus 0y, and this will be equal to 0x plus 1y. So that's where they get the transformation matrix K0, 0, 1. And you can see for the other one, for the stretch parallel to the y-axis, you can see that the x then stays to the same x prime, and the y prime is some multiple of y. So this is going to be x prime plus 0 times y. This will be 0 times excuse me, no prime there. 0 times x plus k times y. So here's where you can see the transformation A is going to be 1, 0, 0, k. Now, what's interesting about both of these is if you found the determinant of them, the determinant of A is going to be k times 1 minus 0, which is k. Same with this one. The determinant of k, or of A, is going to be 1 times k, which is k, minus 0 again, which is k. That's how you can tell that it's a vertical or horizontal stretch. Just take the determinant and see if you get that stretch factor. Okay. They have an example here of, oh, and here's the formula. So then we have an example here of you're going to identify the geometric linear transformation and then write it as a matrix. So this is 1 and this is 3. This is 3 and this is still 3. So if you notice, in both cases here, it's a stretch factor of k equal to 3. And then for the matrix here, my x prime is 3 times x. Y stays the same. And then the y prime stays the same, 0 times x plus y times 1. So you can see how you get the 3, 0, 0, 1. Right? And this verifying the area, you can just look at, this is an area of 3 and this is the area of 9. Voila, that's the stretch factor of 3. Shears are probably your favorite new transformation, because I don't know if you talked about that in honors pre-calc or algebra, but you're taking the top of it and just tipping it. So it's just moving a line segment or a point and just pivoting it off of the two side lines. And the shears are kind of simple to think about as far as depending on which kind of shear you're talking about, parallel to the x or parallel to the y. So thinking of it this way, here's your x plus ky, and the other is the same y. So this one here, your x changes. You still have your original x, and then it's going to be moved k times pn, times that amount. And so there's where you get the x plus ky, and then the y, of course, stays the same. So when you put those together, there's your transformation matrix, 1k, and it's 0, 1. And when I take that determinant, I get 1 minus 0 is 1. And then when you shear the parallel to the x-axis, then you get the same thing, except x prime equals x and y prime equals y plus, x plus ky. So this shear is going to be 1, 0, and this one's going to be 1. Whoop, I did that wrong. So this is going to be x prime equal to x, and y prime is going to be your kx plus y. So this is where you get the 1, 0, k1. And that determinant is also equal to 1 minus 0, which is 1. So you're kind of wondering how the nice elemental determinants here, 0, 1, and -1, and k can kind of indicate what's going on, which I think is very interesting. Now we've hit determinant equal to 1. We've got determinant equal to -1. That's for the two. This was for shear. And -1 was, didn't escape me, but I think it's the rotation. And then this equal to k. Those were the stretches. And we have rotation, stretches, shear, and then there was a reflection in there. So yeah, so when we did the rotation, that's 1. So this is the rotation or the shear. And unfortunately, it isn't unique. For the -1, that I think was the reflection about line. Yep. And I think we're going to see, the only thing we haven't seen yet is the 0. So what's that going to be? Well, we have one to go. One coming up for that. And that's projecting a point onto a line. So when I saw this at first, it really bothered me because what are they even talking about? Points onto lines. But what they're really talking about is landing a perpendicular, like we did with vectors, a point normal to the line, and finding out where the point is that normal would touch the line. Super helpful, because if you know those 2 points, x, y, and x prime, y prime, you can find the shortest distance. Between the point and the line. Remember how much fun we had doing that in higher HL2? We were finding the shortest distance between a point and a line with vectors. So they developed this formula nicely, and it turns into a nightmare, but once you have it, you can, if you know the tangent of alpha, you've got essentially the slope, right? And if you have the slope, you'll be able to figure out all of this transformation business, finding the alpha and so on. Double check the determinant of this, cosine squared alpha times sine squared alpha minus, when you multiply this out, you'll get sine squared alpha cosine squared alpha. So you can see why that's equal to 0. Okay, finding the projection of a point. I'm going to do an example here using that formula. We're going to find the projection of the point, 3, 4, and then we're going to find the shortest distance of that point to the line. I love this because it ties into what we did before with vectors. The slope is 1/2. So if I make a triangle here and opposite over adjacent, okay, is 1, 2, we know that this will be the square root of 5. Okay, so the sine of alpha is 1 over the square root of 5, and the cosine of alpha, theta, is 2 over the square root of 5. So once I know those, I can put those into the formulas that you have here. So if I have, I get the right color here. So I can zip these here, here, all of the signs. You can put those in. You can put the cosines where they go, and you're all set. So let's do that. So if we go, A is the cosine squared of alpha. Cosine of alpha was 2 over the square root of 5, so it's going to be 4/5. Sine alpha, cosine alpha, it's going to be 1 times 2 is 2 over 5. And sine alpha, cosine alpha, again, is 2 over 5, and sine squared is just 1 over 5, which is the transformation matrix we predicted. Now what we want to do is find the projection itself. So remember what this transformation matrix means. It means x prime is 4/5 x plus 2/5 y. And y prime is 2/5 x plus 1/5 y. So once you have that, now what you can do is use what you know to find this projected point. So you know that the point is 3, 4. So that goes into your x, and that goes into your y. So that's exactly what they did. And so they got, we're doing great here, 4/5 times 3 plus 2/5 times 4, and 2/5 times 3 plus 1/5 times 4. So 12 and 8 is 20/5, which is equal to 4. And then this is going to be 6 and 4 is 10/5, which should be equal to 2. So the transformed point 3, 4 onto the line. So this is, if you graph this, here's the line y equal 1/2 x, and here's the point 3, 4, somewhere up here. You are finding the perpendicular to that, and the point where it hits the line is 4, 2. So the last question they ask is, what's the distance between 3, 4 and 4, 2? That's just distance formula. So square root of 4 minus 3 is 1 squared. 2 minus 4 is -2 squared, which is 1 and 4, square root of 5. That's pretty cool that you can find that. The distance between a point and a line using matrices now. Pretty cool. So what you did is you used the slope to figure out alpha or theta or whatever you want to call it. Once you have that angle, then you put that into your formula, which we had earlier here. And once you have that formula, plug those in, you get the transformation matrix. And then once you have the transformation matrix, you can put that into the old x prime equals a x plus by, y prime equals bx plus, or cx plus dy. And then you can transform the point by plugging those in. That is it for geometric transformations. There's one more short video on doing multiple transformations, and I want you to watch that. That's video 3.